We're talking in 6.3 about the concept of circular motion. And this will really later on affect rotational things. So we have to kind of have this down pat. And there's really a couple things that we want to talk about here. The first of these things is that the acceleration of an object in circular motion is v squared over r. Now, what is v? V is the tangential speed. It's the tangential speed. Okay? Now, technically speaking, v is a velocity, right? It's a velocity vector. The reason there's acceleration is because when something travels in a circle, at any given moment, the velocity changes direction. It doesn't change magnitude if it's assuming it's constant circular motion. So this might be spinning at like 3 RPMs. Well, 3 RPMs is the amount of revolutions per minute. We can then figure out the velocity at the edge of the circle, but the velocity is changing its direction. And if I were to show you this or demonstrate it, it would be like a person playing softball. If a softball pitcher releases at the bottom of her arc, the ball goes tangent to the circle. It literally gets launched like this. But if for some reason, this has happened before in baseball, it happens in softball, you like lose your grip when you're throwing. You ever seen a pro baseball player, this I've seen happen before, they'll go to throw it and it'll like fall behind them, and it'll like slip out, or they'll go to throw it and hold on too long and they'll like spike it accidentally, and it's just like your muscles aren't moving as fast as your brain at times. So that scenario here would be like, if a softball pitcher, instead of releasing at the bottom, released here, well, then it would be releasing here, and then the tangent looks like that. So the ball would move in that direction if it were released here. If it's released at the bottom, it moves in that direction. So the velocity is called tangential speed really here because it's always tangent in direction. So if you want to draw your velocity vector in at each location, that's your velocity vector each time. All you're doing is drawing a bunch of tangent rays coming off of the circle. And now that you've taken calc or you started calc, tangents should be very familiar in your language or in your understanding of where it is shown on a graph or where it is shown in motion. And it doesn't have to be a circle, as you know, to have a tangent. Any curve has tangents at any instant along the path. So the acceleration exists because the direction of the speed is changing. Remember, the value of v is not changing for these problems where it's uniform circular motion. It's the direction. It's the direction of v that is changing. Remember, a comes about from either a change in speed or a change in direction of the speed. That's why when the question is asked on like an AP exam traditionally, what things can accelerate or decelerate a car? What's the answer to that? What parts of the car could cause acceleration or deceleration? What are the things that you can use as a driver to accelerate or decelerate the car? Steering wheel, because that changes direction. And then the obvious ones, the brakes and the gas. Right? So there are 3 ways to accelerate a car, not just 2. Most people think the brake and the gas. The steering wheel just changes direction, which changes your velocity vector, and therefore it shows acceleration. Which way does acceleration act in these problems? Which way does it act?
I mean, I guess in the direction of motion, like tangent to the direction of motion. I don't know.
It's not in the direction of motion. That's the common misconception there, actually. Inwards. Inwards. So at all these moments, the acceleration vector is perpendicular to the velocity vector. Remember how a radius and a tangent intersect at a 90-degree angle? That's one of your geometry laws. Whenever a radius and a tangent occur at the same spot, they're perpendicular. All of these scenarios are right angles. You can draw them in if you want, but all of those are right angles. Your acceleration is called centripetal because it is center-seeking.
Isn't it how like sometimes it's the tension in a rope, or sometimes it's the friction?
It can be friction on the car and the tires at a bank turn. It's tension in a rope. It's gravity of an object orbiting a planet. It's the normal force from the wall on the gravitron. Ever got on the gravitron before? It's the thing where it spins really fast and the floor drops out, and then you get sucked up against the wall. Well, the wall is pushing you back toward the center. That's what's giving you that red vector toward the center. Now, if acceleration is directed toward the center, so must the force be? So therefore, our force is always acting toward the center also. So the blue vectors are F. Okay? The blue vectors are F. And that makes sense logically, just like Tristan said. If you didn't have a rope and you were spinning something, or let's say you're spinning something and the rope snaps, it's going to be launched off from the circle. It doesn't want to stay in this circular pattern because of inertia. Inertia tells us what? An object in motion will stay in that motion. Well, technically speaking, when this object is right here, which way does it want to go? It wants to go northeast. It wants to go in the direction of the tangent line. So if I were to literally cut the cord, when it gets here, it gets launched in that direction. The acceleration is what's keeping it moving in a circle. Without that acceleration, without that rope or whatever it is holding it in a circular motion, this object would not stay in circular motion. Okay, it would not stay in circular motion. That's the first formula. The second formula is simply F equals ma, which becomes F equals mv squared over r. So this is the first formula, and then plugging that in for A gives us the second formula. Those are the two formulas we're going to use in this chapter, or this section, or whatever. There's nothing new besides this. Now, the new stuff is going to be conceptually understanding what we're doing here. Okay, conceptually understanding. Your book talks about rounding a curve in a car, which is what Tristan mentioned, and then they talk about orbiting a planet, which is what I was mentioning. But again, as we said, many things take on what is called the centripetal force. Center seeking, centripetal, not centrifugal. Centrifugal is an effect. Anybody ever heard of a centrifuge before? Centrifuge? It takes blood and it spins it really fast so that it separates based on its density, or I think it's density it uses. And you get your platelets, you get your white blood cells, your red blood cells, all this different stuff you can test in different tests, whatever, different arrangements. But the idea is that the desire for the blood to go toward the outer part, or for you to get sucked against the wall in the gravitron, that's called a centrifugal effect. It's not a force. It's very misleading because a lot of students think centripetal and then centrifugal are the same thing. The effect of you sliding outward and going out, that's the centrifugal effect. That's all it is.
All that's actually happening is your direct, like your velocity is going this way, and the acceleration is pulling you inward. That's it.
And the inward acceleration is centripetal, because centripetal is center seeking. Centrifugal means center fleeing, going away from. So whenever you're talking about what's keeping an object in circular motion, it is the centripetal force, which is caused by the centripetal acceleration. Anytime you have acceleration, you must have a net force. You must have a net force. Okay, another classic example that the book talks about is, it's hard to draw, I'll try to draw it. I think I can actually. Here, let me draw on the next slide. So the other one that the text gives and likes to talk about is a tabletop. And that tabletop has some sort of a hole in the middle of it with a rope and a mass hanging at the end. And then that rope is connected to an object here. And what happens is, and this is actually straight out of the lab I did last year in my class, so Parisian Spence, you might remember this, with the pencil. Remember we spun that little thing, that lasso kind of thing, with the rubber stopper? I think you guys did something like that next year too.
Yeah.
Right? You spun something with like a pencil or something between, and there was a mass at the end. That's this problem right here, where this object is spinning in circular motion, causing it to be balanced by the weight of this object here. Okay, this is like a classic problem or a classic arrangement that you'll see for centripetal motion. And again, what are we noticing here is that there's some force keeping this object, let's call this mass 1, and that mass 2. There's a force keeping mass 1 in circular motion. And the direct force is tension. Indirectly, it's the weight of this object here, right? But the direct force is tension. It's a rope. A rope is connected through the table, and this object up top, you give it a spin, and it starts spinning in a circle. Why doesn't it shoot off the table? Because there's tension in this rope that's keeping it in circular motion, and the tension in this rope comes from the weight acting on the rope at the bottom. So it's really the weight of mass 2 that's keeping this in circular motion, but that's an indirect effect. The mass is causing tension, the tension is keeping the upper object in circular motion. Which is why when we draw a free body diagram of this, mass 1 would look like this. Here's mass 1. Its motion is like this, and I'm going to just put it in one spot because I really can't draw in all these different positions. But right now, mass 1 has a force acting toward the center. That's what it has, a net force there. And that's a force of tension acting on it. And then if I were to draw mass 2, and technically mass 1, has weight going into the page. Do we see that for mass 1? Mass 1, its weight, I'm drawing a bird's eye view of mass 1. Think about this perspective. I'm drawing a diagram from above on mass 1. The tension acts toward the center. The weight of mass 1 would be acting into the table, which in this case is into the page. So I can't really draw that vector acting into the page right now. Does that make sense what I'm saying? Okay, I can draw it with an X technically if I want to. There's a way to draw vectors with an X for three-dimensional. So this would indicate that there's a force acting into the page. But you know what? There's also a force acting out of the page, the normal force. And weight and the normal force are balanced. So I don't really care about those two forces because they're not affecting the problem. But the second mass would have its weight pulling down, and it would have tension pulling up. Okay, so a problem like this, we would have two equations of motion. One would be a radial or circular equation of motion up here, and the other would be a vertical equation of motion only. No horizontal equation of motion here. Okay? Let me see real quick. Okay. So your textbook likes to take the adoption of everything acting out of the circle forces are considered to be positive, and every force acting into the circle is considered to be negative. That's the general adoption it takes. But you could do it either way. If you want to call into the circle positive and out of the circle negative, that's fine as well. It doesn't really matter which way you choose. Now, what does matter, though, is the sign of your A value, your acceleration itself. So let's look at this first example. This is on page 135. Okay, we're going to look at sample problem 6.04. It's a bicyclist. I'll draw it on the next page. It's a bicyclist going through a loop-de-loop. That's all it is. So the bicyclist is at the bottom first on the bike right here, riding the bike, and then the person goes up, goes around the loop, and comes back around and ends up over there. And the question is to investigate the forces acting on the bike as it travels through the loop itself. As it travels through the loop itself. So, the first position that the question wants you to investigate is at the top up here. I'm going to draw a box just to see here. When this bike is at the top of the path, right up there, this is the first question it wants to ask us. So, again, when an object moves in circular motion, which way does it want to move? Which way does it want to move? Yeah, it wants to move out of the circle, away, tangent to the path, but away from the center. So as a result, which way is the track pushing on the bicyclist at the top?
Into the cyclist.
Very good. Into the center, or cyclist. Very good. So the normal force from the track is pushing toward the center there. What else is acting toward the center?
Gravity.
Gravity in this case. So both of those vectors provide the centripetal force needed to keep this object from literally launching off at a tangent or away from the center when it's at the top there. So when we look at a problem like this, we have to consider the fact that we've got, and I'm going to draw toward the center positive because I got used to that. I'm reading your book and you could do it either way. The reason the book calls forces outward positive is because they like to measure the radius as a positive going outward. I don't think it matters, and I've never had a problem with it this way, so I'm going to adopt this method that I've used. So the way I would write this is this. I would say the sum of the forces centripetally or in circular motion equals MA, but A is really V squared over R, but A is really V squared over R. And Fc is really the sum of those forces, and we have two of them acting toward the center, Fn and Fg. So if you're looking at the example in the text later on, you're comparing it, you're going to see what the book does, and they label this as negative. They label this as negative, and then they label this as negative. Because they're saying, well, if the acceleration is toward the center, and they're considering away from the center as positive, then it would make your acceleration negative. So this would be negative here, negative here, negative here. So is there any difference really? Mine are all positive. I personally think that pulling toward the center positive makes life easier for you in the long run. Okay, that's just my opinion. You can choose the other way, it doesn't matter. But I'm just giving you my opinion.
So the only time centripetal acceleration is 0 is when it's not moving?
Meaning when something is in circular motion? First, for centripetal acceleration even to exist, it's got to be in circular motion.
Yes, yeah.
But if it stops in circular motion, it's not in any motion anymore.
Right.
Follow me?
So
Anytime anything is going through a curve with any velocity whatsoever, there absolutely has to be AC.
I'm saying like the only possible scenario where AC is 0 is when it's not moving at all.
But then it's not circular motion. Think about
Right.
it. It's not motion at
So
all.
then
So any problem that involves circular motion is moving. So inherently,
you're gonna have A.
precisely.
Okay.
There's always going to be an A in these problems, or else it's literally not moving, and then it's not even in circular motion at that point. Okay? It's a good question, though. I like what you're saying, what you're getting at there, because you notice that V is the only thing that can be 0 there, because M can't be 0. Anyway, so this is the equation of motion at the top. At the top. How does it differ at different spots? So let's choose other spots that make sense. Let's choose the east and westmost point of the circle, and let's choose the most south point of the circle here. So how would it differ? What do you think? Let's put them over here first. Now what is it going to be? Draw your free body diagram of that. What acts toward the center still? Give me more specifics. What force acts toward the center still? Normal force. It still pushes back against you because you're pushing against the surface.
For problems where it's like a plane, what force is acting toward the center? Or if it's like a plane.
Lift and drag force. Depending on what you're doing. You're talking about a plane that does like a loop in the air, right? Or barrel rolls and stuff. That's your lift and drag force. If it's going this way and it pushes you toward the center, that would be lift force in that case. If you were nosediving and doing a loop like that, it would be drag force then. Drag pushes a plane down, lift pushes it up. There is something called negative lift. We'll talk about that soon, I think. Yeah, pretty soon in this section. So yeah, the Fn pushes toward the center, but what's the obvious difference now?
Fg is opposite of velocity. Sorry, Fg is the direction of velocity.
Thank you. Very good. Fg acts down pretty much. It's acting tangent to the circle. Remember, Fg always acts down. So at the top, Fg and Fn together are providing the circular motion effect, or the forces. So this is the equation at the top there. And then we'll redraw the same thing on the left side here. So on the left side, I still start with the same basic governing equation, sum of the forces in centripetal or circular motion equal MAC. And then on the left side, though, what we have instead is simply Fn acting toward the center only. So that's what it looks like on the left side. Is the right side any different? Is the right side any different? I know the diagram looks slightly different, but my equation, why is that, Chip?
Because Fg is still pointing downwards and Fn is pointing towards the center and it's positive.
So because we're only looking at circular motion equation right now, and we're not really looking at our vertical forces and horizontal forces, we're trying to figure out what keeps it in circular motion. Left or right are the same. So let's jot down or right here. So the left position or the right position, either way, Fn acts toward the center of the circle.
Wait, why are we ignoring Fg?
Because Fg does not act toward the center, nor does it act away from the center. It acts tangent to the path. Remember, only forces that are listed under here are forces that act either away from the center or toward the center.
That's all that is relevant.
Correct. Now, there are other positions along the way that would be a little confusing, like right here. Because gravity, when pushing down, has a component tangent to the circle and a component toward the center. So these other positions along the way, FG will have a component of it, like a cosine theta or a sine theta part, that acts toward the center. Okay, I'm slowly building up to where we're going, okay? And then at the very bottom, when it's here, when it's in circular motion at the bottom, we know that gravity acts away from the center, meaning down, and the normal force still acts up. So my last arrangement, we've done top, we've done left or right. Now at the bottom, though, what would the equation read at the bottom? It would read, yeah.
Like the same as the top, right?
Close.
Or no, it would have Fn going upwards.
Okay.
And,
Fn is toward the center, which is positive,
and Fg downwards.
away from the center, which is negative. Try to be careful because it's very misleading to say up and down there because it is up and down. And it turns out, right, Tristan, that up is positive here because up is toward the center. And down is negative because down is away from the center. But that's only at the bottom. Follow me?
Yeah.
Because look at the top up here. Fn and Fg, we gave them both positive signs, didn't we? And they're both acting down. So it's like, wait, why are they positive? They're acting down. It's not about up or down anymore. It's around into the circle or out of the circle. Okay, that's what we're looking at here. So when we talk about things like bank turns and cars going around bank turns, which we'll look at in a moment, what is keeping it in that bank turn?
Friction.
Friction?
Air resistance.
Slightly. There's another component that's huge.
Inside out acceleration.
Another force. Banked turn. Think about a bank turn.
Centripetal force.
Car going around a bank turn would be on an inclined plane the whole time, wouldn't it? Not a bank turn, not a flat turn, but a bank turn. Normal force, a component of it actually. So we're going to have to break Fn into components now soon. So the problem gets a lot trickier when suddenly the turns are banked. And this is like a very classic AP problem. Car going around a bank turn. Because you're involving inclined planes and you're involving circular motion. This is a big part 2 problem, not a part 1. I mean, I could see it being a multiple choice and making it simpler. But this is a big part 2 problem because you're going to be doing stuff with kinematics, with circular motion, with inclined planes, meaning dynamics. So you're going to have a couple different things involved in a problem like that. Okay, so we'll get to the bank turn problem still. All right. Now, besides that, for this problem, the book then asks you to, I think, calculate something, right? It says, what does it say? Yeah, it gives you the radius of the loop, and it says, what is the least speed that the biker can have at the top of the path to still remain in contact? To still remain in contact. What is the least speed? So let's pause for a second and think about this whole process, okay? The least speed. So we want V to be as small as possible in that circumstance. But we're at the top of the path. So up here. We want V to be as small as possible. So if V is as small as possible, it makes the sum of these guys really small, doesn't it? But can Fg change? Assuming we're on the Earth only. Can Fg change? No. Obviously, big elevation changes it, but we're in a little loop here. It's not a big deal. So Fg is not changing if V gets really small. So what has to change if V gets really small for this equation to still be true? What has to change? The normal force. It's got it, right? So the idea is this, right? And first of all, how many of you got on a roller coaster before? Honestly. I'm not a fan, so I've never been on. Okay, you guys have. I have when I was a kid, but I can't go right away. I can't do motion, it's terrible. I wanted to be an astronaut. If you can't go on roller coasters, you can't be an astronaut. Anyway, so when you get to the top of the path on a roller coaster, if it's exactly the right speed, technically speaking, your weight pulling down is enough to keep you in circular motion. Remember that Fn and Fg both push you toward the center? This is a classic problem for multiple choice. The speed that you need at the top to just keep you in motion and not actually have the track pushing back on you is assuming that Fn drops off and goes to 0. And then V you calculate is the minimum V necessary. So let me explain that again to show you. So if we set this equal to 0 here, and we solve for v, we get fg times r over m, all underneath a square root. That's what v is going to give me at the top of the path. But because fg is really mg, this becomes mgr over m under the square root, which really just becomes gr under the square root. Let me just put a little line here to show you what we're working with, okay? All right. So we're working on the top, not the left, right, or bottom. So at the top, when it's reaching the top there, if your speed is really, really, really fast, you're going to want to move away from the circle. The desire of the object to move away from the circle is greater if your speed is greater. So that means that the track has to push back if the speed is a really large value. And again, that's logical here. If this number goes up by a lot, well, this number can't change, so this number has to go up by a lot. So if I plugged in a number for v as like 10,000, well, then Fn is definitely going to be there in this problem, assuming this number is not too large. But if I plug a number in like 2 for v, then there's going to probably be no normal force. So the faster you're going along the track, the more speed you have, as you go around turns, the more the track has to push back against you. It has to physically push back harder with more normal force if you're going faster. So whenever a problem says to you, find the minimum speed necessary on this arrangement to keep it in circular motion. The minimum speed is the instant when you no longer have the track pushing back against you. And you kind of feel like...
I was going to ask if you were going to feel weightless.
So you have that effect. So let's think about this for a second. Your gravitational pull is toward the center, right? Your desire or your inertial effect is outward. Those two things are going to balance each other there in that situation. So when you don't have Fn there, it's like you and the car are kind of like floating on the track there. You're not pushing against the track, so it pushes you back. You're not falling down with gravity because you have this mv squared over r that wants you to move away from the circle. So those are in a balance there. So yes, it's like the feeling of weightlessness, like when you have with a free fall, or like an elevator that's moving down with an acceleration of negative 9.8. Same concept, right? An elevator problem, we've done that one. When you're going down, you feel like you weigh less. So when you're at the top of the track there, the normal force may not exist if you're going at the minimum necessary speed. So the book gives you G, which is 9.8, R in this problem was 2.7, and you literally just plug those two numbers in. So this is really nice to write down somewhere, like a calculator program, so that when you're doing the multiple choice, I would write object in circular motion at the top of track. Minimum speed, and have that written down by calculator.
Just top, right? Just the top.
Only at the top. Absolutely right. Only at the top. Because when it's not at the top, now here, it can't be gravity. That's the only thing giving you the effect. Because gravity isn't even there.
And this applies to other things outside of just this type of problem, right? Like
Correct. Yeah, it absolutely does. So like a problem like spinning a rope. Spinning an object. I've got one here. I mean, I did it last year, so I guess it's a redundancy, but I'll just flip it around again. I bought a new one actually this year. Do you guys remember the one I used last year? I used this thing last year. Remember this? This one I built myself. Remember this last year in physics? I just attached a bunch of ropes, filled a cup of water, put this here. It was gross. Remember, it was all falling apart, and there was like a rope I attached to the end of it. And we just sat here and spun this like this a couple times with a full cup of water, no water leaked at all. Did you do this in honors physics last year at all? Did you do anything like this with a demo? So Mr. Donchek does a demo every year where he puts a hole punch in the cup.
Yeah.
He fills the cup with water and he spins the cup the whole time, and no water ever falls out. Because which way does the water want to go? It wants to go away from the circle. So as this cup is spinning, the water's desire is to move outward in tangent, but the cup pushes back with a normal force from the base. So it's the same concept here. I'm putting the cup on here, and the cup staying on here over and over again. It's nicer actually to put mass on there because it kind of just slips off the bottom. So the idea behind this is exactly that. And what Tristan just said is that when you get to the very top, you can slow down. And whether you realize it or not, when you're a kid and you're at the beach and you have a bucket of sand or a bucket of water, and your parents or somebody taught you that for the first time, that idea that the water stays in there, it's really weird, you naturally slow down your velocity at the top. You go like, you have to like literally spin faster at the bottom, you can slow down at the top, and the water will still stay in there. Because what's happening is, at the top, the gravity from the water wants to pull it toward the center. So there's enough center-seeking force acting that it doesn't need the surface of the bucket to push back with a normal force. It's the same thing as this. It's like the normal force not being there again, and the seat isn't pushing against you anymore. You're in that limbo stage where you kind of feel like you're floating there. So this would be the exact same solution for that problem with a cord spinning in the vertical plane. The horizontal plane is a whole other ballgame. When you're spinning a cord in the horizontal plane, that's the example you guys did and we all did with our labs last year. That's a different scenario. But I'm talking about spinning in the vertical plane. This is a horizontal plane. This is a vertical plane. Is that clear what I'm saying? Anybody ever see Doctor Who? Doctor Strange. No, Doctor Strange. Doesn't he create a portal? It's always like a vertical plane. Has anyone seen that movie? He does the same way you can jump through the portal, right? He always does like some sort of, that's the vertical plane. All right, anyhow, this generic solution can be very useful on a multiple choice question. You see what I'm getting at here, why I'm trying to help you with this stuff? It really benefits you to do well in multiple choice because you can still get a 4 or 5 in this exam and only get like one math problem right at the end out of 3 if you really do well in the multiple choice. That is the number one way to do well in the physics exam. Like there's 35 questions, if you can get like 25 out of 35 right, you could probably just get one of the 3 math problems right and not even do the other 2 and still get a 5 in the exam. It's very, very, very heavily curved. But that's only because the assumption is that a lot of students really do struggle with the free response at the end of the test. They're tough problems, they're not easy. And you guys saw today one example only of the one with drag resistance or air resistance or fluid resistance there. But again, I'm just trying to emphasize how important these small little tidbits of generic solutions could be for specific problems on multiple choice. And why am I saying multiple choice and not free response? Because free response, you gotta show your work. You can't just put this solution like, oh, because I remembered that it's a circular motion at the top, this is the answer. On a free response, you'd have to do what I did, which is show the equation of motion, drop off Fn, and then go through the process of solving. But on a multiple choice, it doesn't matter, you have to show any work. So on a multiple choice, if this is the problem, this is your solution. Without any work, pull up the program, you've got it written. So have specific cases illustrated in your calculator that we've gone over throughout the year so that you can utilize those to help you. Like the Atwood machine with the 2 masses, one on each side, this is a generic solution for that. If I recall correctly, it's larger mass times g minus smaller mass times g, all divided by the sum of the masses. That gives you the acceleration of the system every time. And that's the generic solution for the Atwood machine. So on the test, I guarantee you, you'll have an Atwood machine problem. So I recommend that you have the generic solution for the Atwood machine written in your calculator.
Where do you write the generic solution? I'm just curious.
I just make a program. That's what I. So I would go into the calculator and just start writing a program. Oh yeah, you have Atwood already in there. Nice. So yeah, it's exactly. Was that right? Yeah, I was right. Yes. I wasn't sure. I looked at it the other day. That's why. So
The same place as the quadratic formula.
exactly. But all you do is instead of entering a program, you just enter text. And then to see it,
You go to edit.
you go, instead of hitting program, if you try to run to Atwood right now, it's going to give you an error because it's just text. It's not going to run a program. So instead, you go to program, and you go over to edit it as if you're editing the Atwood program, and it opens it up so you can see it, and then everything in there is in there. Again, though, don't put everything in here that we've done this year because you're never going to be able to find it. You're going to run out of time. So only the really important stuff, like these generic solutions, that would be useful. Okay? So the Atwood solution is this, by the way. It's mg minus mg over m plus m, where capital M is greater than lowercase m. That's the Atwood machine problem right there. That'll give you the acceleration at any instant for an Atwood machine. There's also a generic solution for the force and tension in the cord. And if I recall correctly, it's, hold on. Oh, Lord. This is where my memory is terrible. Hold on. It's, the denominator, I think, is still, no, it's m times m in the denominator. No, it's m plus m. And this is 2, I can't remember. Hold on. I have it in my notes. Hold on.
Wait, what's this for, Mr. Allen?
This is the tension in the cable for the Atwood machine.
Oh,
And it's like 2, hold on, I gotta pull it up. I wish my memory was better. Remember I talked to you guys about memory? My memory is terrible. Since I've been a kid, I couldn't memorize definitions for anything. Social studies, I was terrible. Because I couldn't memorize dates and names and all this stuff. Oh, it was really bad. All right, general solution for Atwood. I'm doing it in the honors physics course right now. That's why I have the general solution written here. Here it is. I was really close. Okay, I thought I was. So it's G, M, M. That's the general solution for tension. 2G, capital M, lowercase m, over m plus n. Again, where capital M is the greater of the two masses. And for any Atwood machine, common sense tells you, if the bigger mass is on one side, it's going to move in that direction. Okay? That should be common sense by now, right? If the mass is the same, will it rotate? What are you in a state of? Yeah, equilibrium. But if the masses are different, it's definitely guaranteed to rotate in the direction of the larger mass. So this would be a clockwise rotation. Spence, go ahead.
Is that alpha or beta?
Oh, that's A. Sorry, A. I'm writing it quickly. So acceleration, but again, these are Atwood problems. This is not what we're talking about for circular motion. I guess it is in a circle, but all right. Let's get to a second example now for circular motion. Let's get to a second example. Which one do I want to do next? Okay, yeah, let's do this one. All right. So the next backup, sorry. The next example we're going to look at is 6.05. 6.05. It says the following. A modern race car is designed so that the air passing above it pushes down on it, allowing the car to travel much faster through a turn in a Grand Prix without friction failing. So normally, if you take a turn really fast and friction isn't enough, what will happen to the car? You slide out. You skid, right? You skid outward. But if there's a force pushing down on your car, that'll increase the normal force pushing back up. More normal force means more friction. Does that logic make sense behind what I'm saying? So as a result, what do race cars have on top of them? Spoilers. Well, wait, sure, but spoilers are actually the most important part. The example we're going to look at, I'll put equivalent of weight, really, right? And the spoiler works just like an airplane weight, except instead of lifting up, it pushes down. So the air running over a spoiler is actually running over the top at a much lower velocity than running under. This is Bernoulli's principle for fluids. Lower velocity on the top of the spoiler creates a higher pressure, which forces it downward. So with these problems with the race car, when we look at the race car going around a track or in motion, not only is the weight of the car acting down on it, sure, that's the weight of the car, but you also have what's called negative lift. Negative lift. And that's this FL, I'm going to call right here. Okay, so this is the car, and as the car is moving around the track like this, FL is the negative lift. So by adding in FL, it increases the value of Fn. Because if it's a race car, the general assumption, and hopefully it stays this way, is that the car doesn't leave the floor or the surface. If it does, then you could have a problem, right? So the general assumption is this. The sum of the forces in the y direction equals 0 for a car going around a racetrack. Now again, I want you to visualize this, right? I know it's tough. Look, that's the path we're talking about right now, okay? This car is traveling around that circular path, and I'm drawing it like an ellipse because I'm trying to draw a third dimension here. Okay, so the car is going around a path like this right now in the horizontal plane. A circle in the horizontal plane. Now, we know that something has to keep the car toward the center. What is that something for non-banked turns? Regular car, regular surface. Friction. So this is my free body diagram of a car in circular motion that has a spoiler on top of it. So the negative lift comes from the spoiler, the air pressure on top of it being greater than below it.
And so would that, the friction equal mv squared over r? In this case, because...
Absolutely. There's no other forces acting radially or toward the center or away from the center. So absolutely right. So the y direction, I'm going to do the y first at the top. The y direction looks like this. Fn minus Fg minus Fl equals 0. But as Chip just said, the sum of the forces acting radially always equal mv squared over r. Well, the only force acting radially that's acting inward is friction. But here's the thing. Friction is mu Fn. So this is what the equation becomes now. So what am I noticing? Let's take a look and let's think about this, right? I want you guys to understand the math behind it. Take a look at this last equation at the bottom here, right? Let's say we've got a value for v right now. And suddenly, I increase the value of v. Okay? I increase the value of v. Mu cannot increase. Mu is a ratio between the tire rubber and the concrete ground, or whatever ground is made out of concrete, I think. Mu is not going to change. So if v goes up, what needs to change for us is Fn. Let's talk about this now. Keep going. Does it 5 connect? Keep going. Fn goes up, why now? If v goes up, and velocity goes up, it actually increases FL. The lift force on a plane is a function of velocity. That's why when a plane takes off, it only takes off at the end of the runway. It doesn't just take off out of nowhere, right? It has to acquire a liftoff speed for the lift force to be great enough to literally lift the plane off. Lift force is a function of velocity, just like drag force is. Remember, drag force is either kV or kV squared. Lift force, whether it's v squared or v, I'm just generalizing right now, is a function of velocity. So if the car starts going faster, v goes up, so therefore Fn has to go up. But if v goes up, so does Fl. And if Fl goes up, so does Fn. How do I know that? Because look, solve this one up here for Fn. Fn equals Fg plus Fl. That's Fn. So if I start getting a larger v value, that means that the lift force goes up. If the lift force goes up, that means the normal force goes up, which would causes this to go up right here. So the only way to balance higher speeds and not sliding off a track, besides banking the turns, which we're going to see later, the only way to balance that option or that happening is to increase the normal force. But to increase the normal force, I can't just increase the mass or the weight, because the weight is a constant. The weight of this car with the person in it is not changing. Well, technically, fuel is being burned. So your gas tank is decreasing in weight. That's actually a big thing with rockets. I don't know if you realize that. When rockets burn solid rocket fuel, the mass of the rocket decreases dramatically. And it decreases at a rate. Related rates, calculus, related rates. Rockets are, a lot of them are solid. Oh, am I right? Is it both then? But originally, solids were used only. What is it now?
The small one is solid, and then the really, really big one is liquid.
We talked about this in engineering, remember? That's what I had. So I think the premise behind solid rocket fuel was that so the mass didn't fluctuate and move physically, and also because of its volatility, right? It's safer to have solid rocket fuel than it has to have liquid rocket fuel. So they used solid rocket fuel for like a really long time. I think now it's both.
It's both. It's more efficient because liquid rocket fuel is better in space.
It's better in space. So what I'm getting at though, obviously here, is for the car traveling around the track, when it burns fuel, technically it's getting lighter in weight because all that combustion coming out of the back of the car is mass. And mass cannot be created nor destroyed, just transferred. So it loses mass in the car, in the gas tank. So technically what's happening is Fg is going down, right? This number is getting lower because mass is being burnt. The fuel is being burned. So we're actually losing Fg, which means we're losing Fn. So we really need to combat that. So Fl is the one thing that will cause Fn to go up because you have more velocity. Okay, so this whole problem and the whole premise behind it is recognition of the fact that we have multiple forces acting on an object when it's in circular motion. So let's replace Fn with its equivalent expression here. Let's plug that in for Fn in the formula, and this formula becomes mu Fg plus Fl equals mv squared over r. And the problem in the text is asking you to find out what the lift force is. In the textbook, they say solve for Fl. So let's divide by mu. Oops.
So would that be lift force or like a drag force?
It's negative lift, it's called. Negative lift. I know, which sounds crazy, but it actually
It's
is.
not like the same thing with drag, where it's like the weight is being applied.
Correct.
It's intended to.
Correct. It's intended to.
So lift kind of means intended direction rather than just off.
Yeah. Exactly. It's not about up or down. It's about the angle of the spoiler. If the spoiler were angled the other way, it would create lift force. So you know how like airfoils have a certain pitch to them? The airfoils are wings of a plane. Have a certain pitch. The pitch for the spoiler would be the opposite. Because you want to push down on a spoiler, whereas on a plane you want to push up.
When planes land and they drop flaps to landing flaps,
That's increasing drag force, is what they're doing.
because aren't they redirecting?
The flaps suddenly go like this.
Yeah, aren't they increasing
all that
the
air.
drag technically?
No, because
Wouldn't some of the air be redirected downwards?
but the lift comes from high velocity on the bottom. No, really high velocity on the top of the wing. So by changing the angle on the top, you're having more cross-sectional area, which increases the drag force. Does the lift change? It probably changes, but the drag force becomes much more valuable when it does this versus when it's flat. So the drag force technically overpowers the lift force, which is what causes it to start to fall.
When planes land, they fall really weird. Like,
I don't know. I haven't studied aeronautics as much. I probably should, but yeah. What do you mean by fall weird?
Like it's like a controlled rate, in a sense.
That's usually just the computer system that's doing it, though. Yeah. There's feedback loops in that system that say, like, you know, every couple seconds you want to drop a certain amount. So those angles on the wing, that's not the pilot. You know that, right? The pilot does nothing of that. The pilot literally either increases or decreases the amount of knots.
Well, not necessarily. It depends on the model.
I'm talking about like the big aircraft carriers, like commercial airliners.
On the big ones, it's actually the pilot more often.
Is it really?
The smaller ones, it's usually a commander.
Really?
The bigger ones are.
I would think it'd be the opposite, because I would think the big ones you'd want to rely on the electrical signal, not the pilot.
It's easier to fly the bigger ones because there's so much mass that you're moving from control-wise. Like it feels like it has such a fine controller.
So like a small change with a bigger mass isn't as effective as a smaller
It
plane.
feels really like more stuff.
Interesting. That's wrong. So point being here, though, right? We have mu and r in the denominator now, and that's fg plus fl still. And then if we solve this, we can move fg over. We'll get fl equals mv squared over mu r minus fg, which is really just mg. All right, subtract this over as mg instead. Just so everything's in terms of mass. So this is the lift force on a car going around a circular track with a given coefficient of friction. Another thing that might be worthwhile writing down in a calculator program if you're looking at lift force as a generic solution for a car going on a track. Not a bank turn. We'll get into bank turn in our next example, but this is not a bank turn at all. It's going to change dramatically with a bank turn. That is kind of where I wanted to end. So this works out really nicely. So we have the bank turn left for this problem. That's really the only one that makes it a little bit more difficult. I haven't introduced the problem with tension here. Notice that? But it's the same thing. Instead of FF being here, replace FF with FT, and now it's a tension problem. That's the only difference. And with a tension problem, maybe you don't have lift pushing down anymore, right? Because it's a tension problem, you're probably swinging in the air. So that's how it would change that value. But for this concept, I want you guys to start thinking about the idea that all these forces are interchangeable. So really quick, just so you know, is it Monday the trip?
Yes.
Okay. Who's going on the trip on Monday that's here right now?
Us three and
Three?
then Matt.
And then Matt. So Matt's missing 2 classes. So he's the only one missing 2 classes. So next class, I'm going to continue 6-5. I'm going to go into the bank turn. And then I'll probably...
Just 6'5"?
Sorry, 6'3". 6'3", sorry. Honors, different numbers. And then I'll probably do an example or 2 of tension just so you can see what it looks like. Okay, so we'll get to circular motion. If you want to start homework for 6-3, I'll definitely try to assign it and put it on Moodle either later today or maybe tomorrow later in the day. Okay, so if you want to get a head start on 6-3. After this, we're done with forces, which is nice. We'll get into energy and momentum as like the next 2 major chapters, and then we have to get into rotation still. Okay? So this 6-3 is really the last topic for the second quarter. The next test is going to be like 6-1 again with friction. You're going to see it again for sure because it is involved in 6-3. 6-2, which is drag force, and then 6-3, which is circular motion. That'll be your 3 topics for the next test coming up. Is that clear? And then the third quarter, we'll do energy and momentum. And then the fourth quarter, we'll really focus on rotational stuff and harmonics, which is vibrations. That's kind of where we're going.
This is so
But
good.
here's the good part, really, here's the good part. If you can master mechanics and dynamics and circular motion and energy and momentum, the topics that are the easier ones, sorry, it's a lot. But if you could do really well on those, the rotational stuff is really only like one problem of the part twos. And it's a couple multiple choice. And the harmonics might be one problem in part two. So what I'm saying is, we really want to focus on mastering the beginning stuff, and then at the end of the year, we'll focus on that. And that other stuff later is all integration, which we haven't done in Calc yet, or you guys haven't done in Calc yet. So it works out nicely that it's in the fourth quarter, actually, because we're going to do all integration for that stuff. So it'll be a little bit tougher in that sense, because it's more calculus.
We're starting integration now, so.
Yeah, you were saying you're doing area under the curve and stuff. There's just a lot of formulas that you'll be using, and then the logarithm and the exponential function are applied a lot. Hey, take more banana bread if you want. If anyone wants more, take for the road, feel free.
So good.
Like it in the end? Yeah.